Thank you, everybody, for coming, both in person and online. I'm Chris McLennan, I'm the president of BAGS, and we are pleased to welcome you to our April talk featuring Dr. Michael Wilt. He is a geophysical affiliate at the Lawrence Berkeley Laboratory, where he works in deep reading electromagnetic technologies. He's been active in really geophysics, not only geothermal, but geophysics for his 40-year career, more than 40, right?
Close to 50.
Yeah. He's been all over the place, genomics, both national labs in the Bay Area, EMI, which is where I met him as a senior graduating and going into grad school, and Schlumberger, and he has ties with the Bay Area because he graduated from here. He is also a former president of BAGS itself. So again, thank you all for coming. Thank you for continuing your membership with BAGS. And Mike, let's go ahead and take it away.
All right, I'm seeing dogs barking. I'm already getting a review. Okay, so this is we're going to talk about geophysics for geothermal exploration. My view, and a lot of other people have other views. This was actually a great pleasure and a lot of work to put this together, but it was an interesting journey. So we'll have a walk down memory lane here. I can just there we are. So some context. First of all, when I graduated from college, undergraduate in 1973, and the world was used to cheap oil at that point, $4 to $6 a barrel. It's been that way for a long, long time. And at that point, because of the Arab oil embargo, it spiked to $15 a barrel. And if you look at what the real price is given by the blue curve, that's equivalent to like $90 a barrel now. And it's really quite expensive and a big shock to everybody's pocketbook. Not only was the price high, but the supply was limited. So we were in no man's land. So we were trying to find other sources of energy, and the newly formed DOE, which was formed in 1975, I think, was started to look at geothermal. So there was geothermal energy in 1975. I'm going to look at this through two windows. One in 1975, kind of when I started working in this area, and another 2023, years later, how we do the same things and how things have changed. There was power then. Large Oil, Italy, and the geysers were the only two power plants around, together maybe 50 megawatts. It was thought that geothermal would have great potential, hot springs everywhere, lots of volcanoes. So all you got to do is drill the holes, get some free water, run the power plant, done, right? And it turns out it was abundant. So you see the Pacific Ring of Fire up there, all around the Pacific, western side of North America and South America, eastern side of Asia, and down to the Pacific. There's geothermal and volcanoes everywhere. And if you look in Europe and Africa, mostly at the plate boundaries, you see sizable geothermal accumulations a lot of places. So, all right, we got something to work with. If you look at the US, there was a lot, right? If you look at the Western US, Nevada is just full of hot springs. California is full of hot springs. Oregon, even the Gulf Coast has geopressure. So there was a lot of potential here to produce a geothermal. Keep in mind, this isn't going to power your car, right? So this is more about electricity, right? But maybe we were thinking even back then of EVs, I don't know. But in any case, we're looking for alternative energy, and really oil and gas was powering a lot of the electricity generation at that time too. Okay. So by the 70s and 80s, the US was the most heavily involved in domestic and international geothermal exploration. I'm not sure when you entered the fray, Bill, on this stuff, but I was there and I knew all of the majors. This is even before you came on board. You were Unical, Greg, but I worked with Shell, and Chevron was around, and Unical was big at that time. I worked at Phillips as a summer intern, and Sun and Hunt, a ton of other ones were doing that. They were doing most stuff conventional oil and gas, but for geothermal. The R&D was led by the government labs, the universities, and the USGS. So we did most of it, and you can see that really provided a lot of dividends in the long run. There was a lot of missteps early, But as we learned more and the technology got better, we got better too. There were also a lot of small service companies. I worked for Geonomics in Berkeley. There was Zong was right around there. There's a bunch of other ones, but notably, Schlumberger, Halliburton were not involved. Too small of a market for them, or too weird, I guess. So what was the toolbox in 1975? A lot of field geology, some airborne, looking for the hot springs, the lineaments. You could do that back then. Not much in satellites, but mostly airborne surveys. Geochemistry, it was in its early phases, but we were learning a lot how to analyze hot spring water and other surface springs to find out if there was a thermal source and what the temperature. Geothermometers were real big back then. A lot of shallow drilling. A lot of the earliest exploration, successful exploration, was done by Magma, and they just frigging drilled. They just went to a spot that had hot springs and they drilled. They were known. There was a famous story, and I don't know if it's true or not. South end of the Salton Sea, it was a basin. People were drilling for oil and gas. They ignored the volcano. They went through the cap rock, and the thing exploded. And they just watched the water come out at 300 degrees C, and they just watched their drill rig melt in about a half a day, right? So it was interesting. So as I said here, you also have luck. You needed a lot of luck. A lot of there was no really clear model for how to find this stuff or what it's supposed to look like. It was largely target based. And I'll show you what I mean by that pretty soon. Now, the geophysics toolbox was interesting and a little bit weird. Seismic methods didn't work very well. And these hot spring areas and the volcanic areas, reflection and refraction was not very useful. They wound up with a lot of expensive bad data. Micro earthquake surveys were good and useful, right? Seismic, maybe. Seismic noise surveys. I remember when I was working at Geonomics, that was a big deal, right? People would do seismic noise. They would just sit there with seismometers and measure the background noise, thinking it's coming from a deep thermal source. Well, not sure about that. Potential field methods, gravity was common, mag was common. SP surveys were just starting to emerge, but the gravity and mag was very, very simple. All you could do was these fixed bodies like cylinders and spheres and stuff like that, right? Electrical, they were starting to be well used. Roving dipole resistivity, I'll talk about that one. That's one of my favorites because we did that a lot when I worked at Geonomics. And it was the dumbest thing I've ever heard of in my life, right? And you'll see that no possibility of really working. Tellurics and MT were emerging, but the data was lousy. So I was brought in because my master's thesis was on tellurics. Success?
Maybe.
Oh, no. You want to check up? We're gonna do a little technical assistance here.
All right, that is working.
Excellent. So Chris saves the day, at least temporarily here now. So I'll stop here in a minute or two, and then we'll go through what we're going to do for the rest of the talk. This memory lane stuff I found was an interesting path to go, because a lot of stuff, as I remember back then, was quite difficult to do, and certainly difficult to do it right. And the results were, let's say, not overwhelmingly great. Sometimes it worked. So if you look at geothermal systems, there's a lot of physical property changes that give you something to look for. Density anomalies, however, sometimes they go in both directions. So for density, shallow mineralization, density goes up. Intrusive bodies, density goes up. Fractured rock, density goes down. Thermal alteration, density goes down, right? So resistivity anomalies, outflow zones, altered rock, resistivity goes down. Hot spring areas and high temperature, resistivity goes down. Steam filled fractures, resistivity goes up. Dynamic, that's more interesting. A lot of these systems have a lot of DC SP potential. I think this is really one of the underutilized techniques for exploration, right? I think always has been hard to get good data, but a number of cases, they just measure the frigging voltage, and you can often see where the sources of the flow are. And if they're deep, you can see that. Micro earthquakes, these things just reverberate, they crack and they pop, and they're always been good tools, and they're still good tools for that. Magnetic anomalies, high susceptibility, high magnetic anomaly, sometimes volcanic cover, high magnetic anomaly, demagnetization due to high temperature, low magnetic anomaly. You can see both in geothermal. So you have to kind of know how to navigate your way through these physical property changes and really narrow down what you're looking for in order to make geophysics work. Some targets. Now this is kind of fun. So early on, resistivity was thought to be, it had a nice correlation with thermal zones. It was a great place to see. It turned out it really saw the leakage, really the hot spring and the thermal alteration of the surface rock. But this was the great panacea. It came from New Zealand. They were doing it a lot. So the upper graph here is from New Zealand right here. This is from the North Island, and you see these low resistivity anomalies. They're associated with hot springs, right? And so a lot of the drilling and production in New Zealand was coming from the DC resistivity. Doesn't always work. The bottom is the SP anomaly, as I alluded to, that Bob Corwin collected at Cerro Prieto geothermal system, which is an enormous geothermal system. It now produces close to 850 megawatts, and the SP anomaly is gigantic. And you'll see coming up that this SP anomaly is very close to some other anomalies in the field. It's pretty cool field. Salton Sea, gravity and magnetics are huge there. So I was a student at UC Riverside for masters, and that was their playground. So Sean Beeler collected the gravity and magnetics at the south end of the Salton Sea, and the anomaly was gigantic. And it's due to A, intrusives, and B, a lot of silicification in the geothermal field. And the magnetics were agreed. They have cones, but there was also a lot of deep sources. And so you see a lot of targets here associated with the geothermal, but not necessarily with the geothermal reservoir. It's usually the outflow or some densification of the surface rock, or maybe a volcanic. It's not always so clear. The SP, I would argue, is a flow dynamic related one. So what didn't work? So this is a roving dipole apparent resistivity map. I worked for a company called Geonomics that made a living doing this stuff. It's the dumbest thing I ever heard of. Basically, you put a source on the ground and you measure the voltage everywhere. And you calculate the apparent resistivity due to that source and you plot it on the map. And then you move the source around and you do it again, and then you do it again, and then you do it again. Typically, they did it 6 or 7 up to 10 different times, and you have 8, 10 different maps, and they look a lot different from each other, and you overlay them, and where it's low on most of the maps, drill here. I mean, that's as far as the analysis went. We were trying at one point when I was at LBL to fit the data with a 2D model, and really hard, really difficult. It was I call it the light bulb theory, as if you had a room full of stuff like this and you had a very dim, like 1 watt white light bulb in the corner, and you measured the lumens and you're trying to map the furniture with a series of 1 watt light bulbs. It doesn't work very well, right? Seismic noise. What the heck was that? Basically, you put all the stuff around these seismometers and you measure the background noise. My guess is you got a lot of drill near freeways. You got a lot of that, right? So not a smart MT. We were starting to do a lot of MT, but the data was so lousy that our analysis was so primitive, we didn't get much. All right, so let's move on. So I allude to this earlier. I started doing geothermal when I was a student at UC Riverside. My master's was started in 1973. And I worked for Jim Combs, who was he was my director there. I lived in Texas for a year, oddly enough, right? So I was on Telluric at the Dunes geothermal field with my master's degree. After the master's, I was hired by Phillips. Phillips had as an intern for summer, and they did all the stuff all around the Western United States. And so I visited, I don't know, a dozen different prospects, sampling water, measuring gravity, doing whatever they asked me to. And that was geothermals in gorgeous spots, beautiful spots. I was amazed at how pretty the spots was. And afterwards, I was then hired by Geonomics. And Geonomics, I pretty much brought Tellurics, and we started the MT program at Geonomics when I was there. I was only there for less than 2 years, and I was hired away by LBL, who was growing their geothermal division. And Geonomics was a crazy place. For one thing, a student right out of school, I was their expert on MT and Tellurics, and I didn't know crap, right? So Just to let you know. So I was at LBL for 7 years doing all geothermal. We did Northern Nevada EM and largely the Cerro Prieto DC resistivity and a bunch of other things, including SP and a lot of what we called it control source frequency EM. Went to Berkeley basically after I finished LBL at 83 and finished in 88, I think. PhD project was EM surface versus structure, time domain, not too much geothermal. My first job was at Livermore. After that, we did geothermal there. I was working with a borehole tool that EMI built, and we did a project for Livermore at the same time. EMI actually built me a crosswell tool at the time too. And I did some SP. I was lured away by EMI in 1997. Ed Nichols sitting back there was the president at the time, and he was the guy I went to Berkeley with. And so about half of our stuff was geothermal at EMI, maybe more than half, I think. And they were involved in the MT system development, and we have a couple slides on that one. There's some other things that the EMI was founded on an induction coil and the MT1 system. And I was involved in doing a lot of stuff with their borehole tools, including some stuff with the Japanese. And we built our own when I was at EMI. We built two of them, right? This a crosswell tool and a single hole geothermal tool called Geobuild. So EMI was then acquired by Schlumberger, and I dropped geothermal in for the next 12 years and mostly worked on oil and gas stuff. And now back to the LBL, a lot more geothermal. So the span is 50 years. I had a front row seat. So I saw a lot of stuff come and go, right? So it's been an interesting a career. Amazing how much geothermal went. All right. So back to what has happened in the 70s and the 75 to 2000. Department of Energy, they led the technology development centered in particular thermal areas. So a lot of the technology was done with a goal in mind of developing the geothermal potential of particular sites. And usually the government funded a lot of the heavy R&D lifting, and there was some company associated with it that did the harvesting, if you will. So for example, at Roosevelt Hot Springs in southern Utah, right here, DOE and University of Utah did also, and USGS did all sorts of stuff there. But Phillips owned the leases at Roosevelt Hot Springs, and they are the ones who built the power plant, right? So, but a lot of the geotechnical stuff was done by University of Utah and the USGS before that, right? The same for the geysers. Unical did all the heavy lifting, but the USGS did a lot of stuff there as well, especially all the micro earthquake. You can fill us in there, but Unical didn't publish a lot of stuff they did on the geysers, but other people did. I remember Isherwood did a really nice gravity study there. There was a lot of good background solid work done by US national labs and the government, and this went the entire spectrum of stuff that we looked at. The seismic techniques, the EM techniques, the thermal techniques, all of it was done usually with some sort of a government backing, and there's usually some rider associated, Unical or Chevron or Phillips associated with the particular area that harvested all the good work and drilled the holes and made some money. So, but with that going, this stuff basically worked. 20 to 25 years of funding and some smart people working on it, we figured out how to do this stuff. So I have two examples. One of them was Cerro Prieto, which I worked on for a number of years. And the second one was what's happened to MT over the last 25 years. I remember I did a lot of MT when I was at Geonomics. We had 4-channel magnetic tape recorder, and our little generator. MT is 5 channels, okay? EX, EY, HX, HY, and HC. So we were supposed to only measure the 4 because we didn't have another channel on our tape recorder. We had a little generator there, some ethical filters. You wired everything into the truck, and you monitored stuff with strip chart recorders, right? And that was state of the art back there in 1975, right? You got good data with that, you were frigging genius and very lucky. We did once in a while. Okay, Cerro Prieto, back to there. Cerro Prieto is in the Salton Trough, which is this pull apart basin in the southwestern part of US and Mexico, right? It's in the Mexican side of the border. There are a number of geothermal fields, Cerro Prieto, Brawley, Salton Sea, East Mesa right here, dunes right here. See that? That's where I did my master's, right? You have Heber and a number of fields associated with this. The big ones are Cerro Prieto, which is about 800 megawatts right now, and the Salton Sea, which is about 500 or 600 megawatts, right? There's an active plant in Heber, there's an active plant in East Mesa, but they're quite a bit smaller. So what happened there? So let's go back here a second. It was our ideas, they had started developing this, the first power when we got there in 1977, they were at 37 megawatts of power in the first Cerro Prieto 1, they called it, right? And they wanted to, they didn't have really the expertise to do much more. They wanted to pull in all the US to figure out how this thing worked. They knew it was bigger than they could deal with right then. And so and we loved it. This was great stuff. As far as geophysics did, we did freaking everything and it all worked. SP, gravity and gravity monitoring. This was the first field that I know that did precision microgravity. And she could see sizable changes. Rosie Cornell was doing this. Magnetics, we did a big magnetic mapping. They already had DC magnetics, and that turned out to be really interesting. I was working with Norm Goldstein and Razo, and I did the 3D fitting of the magnetic anomaly. And we found something fairly cool. The DC resistivity study was led by me. I have a slide coming up on that. MT, this was the first study by Gamble and Gubal to show remote reference data that was published. And they had on the exact same line, I did the EM resistivity, the DC resistivity, and they found very similar. They could use my model, in other words. Active seismics, there's a lot of micro earthquakes there, and we did it with CF. They did seismic reflection here. And they CFE. Pardon? It's Centro Federal de Electricidad, which is the electrical utility and also sponsoring agency in Mexico. Thank you for asking a very pertinent questions here. People would have no idea who these people are. And a lot of geology, we had half of our group at LBL working on this project for about half of the year. Marcelo Letman led it. We had Al Truesdale sitting there full-time from the USGS doing the geochemistry. What a brilliant guy. I just love that guy. And I learned so much from these guys. So an example, it all works. So this is the dipole-dipole resistivity. This is done right over the heart of the field. These are 1 kilometer dipoles, right? So we would, it took us a while to figure it out, but I was able to do this in about a week, right? The field crew was brilliant at the time. They laid all the wire out, and this was number 10, big TX wire, and I'd use it at the receiver end and at the transmitter end. And they'd lay out 4 dipoles at one time, and I'd run them into the signal averager at the van, and I sit there and stack data like crazy, 40-second period. It usually took, for the really long ones, it took several, maybe 4 hours to get some good data. And I had to get good data. I needed 1% repeatability. But this was tight. It was excellent, excellent quality data. I had to go to really long periods, 40 seconds, because otherwise it was so conductive, the signal would EM couple everything and you wouldn't see anything. It'd get smaller and smaller as you did larger distances, and you'd lose the DC part of the signal. So the data was, I fit it by hand with a code called Resist2D that was developed by Abhijit at Berkeley. And this, as far as I know, was the first detailed effort. This took me a long, long time, but I eventually fit it very well. And the model, remember, I had geologists everywhere. They knew what the field's supposed to look like. So when I did the model, I go back and forth with them, and the model I came up with fit damn well. Couple things. First of all, I was looking for a resistivity low. It's not a resistivity low. It's a resistivity high. So why is that? Well, it turns out that a lot of the rock was silicified, basically with thermal fluids flowing through the reservoir as they produced it and depositing a lot of minerals, right? And then a lot of the water coming in was fresher than the water on the outside through the hot springs. And so the resistivity was higher than the background. Quite a shock, right? I repeated the surveys 5 times. We had two, this was the main line, but I had a second line as well. And I was seeing the reservoir region increasing in resistivity, this 4 ohm meter, especially at the top here, was increasing at about 5% a year, and I could measure that pretty well. It wasn't a problem. I don't want to blow all my time with my own slides, but I was able to model it reasonably well too. You could see the resistivity increasing, and my feeling is what's happening is you were, like all geothermal fields, you were losing pressure. Basically, you were producing more water than you were putting back in, and because of that, the steam fraction was increasing, and so you were increasing the resistivity due to the steam fraction increasing. Nueve Leon magnetic study. So Norm came to me with this. Norm was my boss. I don't know if he's on the line. Hopefully he's on the line here, because he came to me with this anomaly. He said, why don't you try fitting this? Because it's right in the middle of the field and nobody knows why the magnetics is so high in the place that we're not. Yeah, it seems too big. I don't know what's going on here, right? So I fit it with a 3D M prism. It's a code developed at UC Berkeley, again by hand. And there was no other magnetic anomaly in the area. It was this is it. Stood out like a sore thumb. So I fit it with a 3D prism at 3.5 to 5 kilometers deep. This turns out to be the smoking gun. This isn't intrusive. This is the thing that really powers the entire frigging system. All the heat is coming up through it, probably periodically dike intrusion into this intrusive body, and it's providing the heat for the geothermal anomaly. So, and it comes out to be exactly the same spot as Bob Corwin has the SP anomaly along the western side, and a number of other things that we found out that make sense. So it was an interesting case. So the schematic model, here's my intrusive sitting right here. We have water coming from the Colorado River and from local water pulling into the field, and you're producing from the top. It's a very simple, you have some hypersaline brines at the bottom, but most of the geothermal in fields around the world is pretty fresh water. It's not as salty as you saw here in the Imperial Valley. It's another thing that clouded me, because a lot of the fields in the Imperial Valley, it's the resistivity is lower than other parts of the West. So it was a great environment. Most everything worked. We got great support. The only issue is we had to cross the border every day. So I would be out there, and I was living in, I had to live in Calexico or El Centro and cross that stupid border, which took an hour each way every single day. So I was there at 5 in the morning and again at 8 o'clock at night every day. I didn't sleep much during that week or 2 weeks that we did every year. The first several years, they let us stay in Mexico, but DOE said, no, you got to stay in the US. We're going to fund you. So that's what happened. The prediction started at 37 megawatts as we got there. It's presently 820 megawatts with 5 separate power plants. So it's a sizable resource.
How deep is that magma?
We don't know, but the intrusive is 3 to 5 kilometers. So below that, you would think magma is there, it would be demagnetized, and that's something to look at. But I think that intrusive must be, the magma might be 6 or 7. That's very speculative. I have no idea. It wouldn't be some bubbling cauldron down there, I don't think, anyway. They're very much of a cartoon. So what's our toolbox in 2023? Here's where you guys should start to chime in here, right? Okay. So the field geology, again, is way better. Satellite imaging is very common and useful. A lot of airborne surveys of various types. The geochemistry is in a different world. Water and gas and soil sampling are done routinely, and the analysis is extremely sophisticated. I worked with the guys at Geothermics. They have a couple full-time geochemists, and they probably spend half of their budgets on doing geochemistry around the world. And they pretty much know before they drill the first shallow hole if this is a viable prospect or not. They don't always know where the reservoir is, but they know there is a reservoir down there. Shallow drilling, heat flow, thermal gradients, we still do the same thing, but we're a bit more selective. And geophysics, instead of target-based, we are now model-based. In other words, with all the experience, we have some idea what the system should look like geologically, and we start looking for that, not just targets as we were doing before, right? We also are doing more monitoring now. Bill provided me a couple great slides on microgravity for monitoring, but more and more you'll see things are changing in with time with any geothermal field, and there's stuff for us to watch. Experience. I don't know if Geothermics is on the Zoom call, but Geothermics has 40+ years of experience in geothermal, right? These people have been everywhere and they've done everywhere, and this is how you find it in the present day. So what's our toolbox? What do we use geophysically here? Many of the same methods, but a lot differently than we did before. The seismic methods are a lot MEQ now. There are a lot more bases, and Roland did some great work in the geysers where he's showing micro earthquake data, and he was getting a lot of porosity information and saturation information from the micro earthquake data. And I think that's a lot very common these days, right? Potential field methods, gravity and mag are common. The coverage and quality are way, way better. Things like GPS location and elevation. I remember collecting gravity data and doing these hand-done terrain corrections. Anybody ever do those? What a royal pain in the butt, man. It took forever to do one single station. Now some computer program does them perfectly every time. And you know the elevation and you know the location of all of these things. It's a different world out there with potential field. Absolutely. The entire interpretation and processing is always also much different. A lot of joint inversion goes on because the big pull in with gravity is the fact that you're sensitive to density. But the big pull back is the fact that it's so non-unique. So you need other data to be able to put where your density distributions are. But if you have it and you can narrow stuff down, it's a powerful tool. And a lot of it's also a nice tool for management. Things are changing with density in the field over time as these fields do water. The electrical methods are dominated by MT these days. When I was at the lab, we did controlled source EM. I did a lot of that, right? Limited depth of exploration is probably the main thing there. 1.5, 2 kilometers at most, and you have to really push to do that. MT does that in the sleep, right? It's really easy. And the equipment for MT is way better. We'll go about that in a moment. The airborne ZTEM is also a very nice tool now to use in combination, because here you can quickly map the upper 50 or 100 meters and combine it with something deep and do your statics at the same time you map the surface features. It's really quite powerful. Borehole tools is where I did a lot of the most recently work, and that is with the VEMP and MAIL tools are built by EMI for Japan. And these are still alive, and we're about to use one of these at the Ford site. GeoBuilt is a system I built with Ed at EMI, and I don't have any data. It's a geothermal tool. Don't want to show data because I have too much other stuff to show, but it was a 3-component source, three 3-component receivers. We never finished the bottom one, but 2 meters and 5 meters. And so you can map around the well in 3D, especially known for fracture delineation. We used it in Dixie Valley and sees the fractures just fine. We fried it when I tried to use it in the geysers. It came up in pieces and we never rebuilt it, right? But it was quite an amazing tool when the surveys I did with it. Let's see what else I have, right? Now the interpretation these days is more model-based. And you're looking for a common model to explain a lot of the data at once, and that model has to make sense geologically. Okay, an example of technology improvement, a magnetotellurics. In 75, as I said, dynamic range default was 12 to 16 bits, local generator, very, very noisy. Data processing later at the lab, you just made sure the data coming out of your strip charts look reasonable. EX looked like HY, etc. That's all you had. We ran filters. We had narrowband filters, the Ithacos, and we tried to get coherent signals in each band. When we did that, we're good to go. We recorded the data and hope we had a long enough recording to get some signal out. That's it. We had squid magnetometers. Talk about pain in the butt, man. Basically, these were liquid helium cooled. And so you had to have your little cryogenic labs with you at all time, a supply of liquid helium and liquid nitrogen, because they had ice plugs. And they would last, I guess, a week to 10 days, but if your field was longer, then you had to find the source of helium, right? Real pain in the butt. So a lot of bad data, and this was common. This wasn't, it was done that 1975, that's what we had, and it was just emerging now. A lot of people were interested in MT in 1975. One of the biggest surveys we did, it was actually for Unical up in Mammoth Lakes. And that was probably among the best data I had, but it was still so hard. So what improved? Well, the first thing improved was remote reference. And Ed Nichols had a piece of this because he got to feel what remote reference was all about. Gamble and Gubal had the ideas that if you recorded two stations simultaneously, that the noise fields at the stations would be different. And he was right. And when he did cross correlation, they were able to get rid of the noise. So if you did cross correlation and you stacked over time, you could get signal even in poor and low signal bands. So it solved the main problem, right? Basically, MT is not a uniformly powerful spectrum. Between 0.1 and 10 hertz, there's almost no natural field electrical data. But in turn, what Ed found out is there's a lot of seismic data. So a lot of the seismic micro tremor motion and the change, because they're moving the coils, would really contaminate your recordings with basically, it turned out to be acoustic data. And if you had a different site, then the acoustic data was different. And so you're able to cross correlate them and get rid of that. And that helped a lot. The second thing also Ed had a piece of, that was the MT1 system, which he and Ugo designed and built. Back then, Woodward Clyde had a good system. And they had huge monstrous fans, and they had basically these LSI computers in them that they were collecting DAX, fax computers. They're collecting the data. They would use RF telemetry, squid magnetometers, all this fancy stuff. But it turns out it took them a long time to get good data because they had this huge generator and all this power that they were using, and the noise field was just gigantic. The MT1 kind of solved that. It ran on batteries, a little basically analog filters. The first one is only 16 bits, right, Ed? Yeah, and then but 16 bits, battery power. And what he liked about it best is that it improved about every 3 months, because that's when the new laptops would come out and they would be faster than the old laptops. You could do the processing right there on site. And you had a second station that you, with cabling initially, that you did remote reference with. So this system was founded, EMI was founded by this system primarily with a huge contract for JERD in Japan. They brought a ton of systems and they just crossed the country collecting MT data, and they collected a lot of good data. Well, that led to the other thing that EMI built were coils. No squids needed. And that we usually have 2 coils, the BF6 and 5, and then the BF4. You needed both of them to cover the band. Now you can cover the band with just 1 coil, I think, right? It turns out that the low frequency signal kept getting larger and larger at low frequencies, and so you don't really need an ultra sensitive coil back then. Signal would get bigger and bigger. The network systems came in 2000 to 2010, where the node systems, EMI, Phoenix, Zong, Medtronics. Medtronic system, the data logger looks like this right now, a little suitcase and a little bit of battery. And your field setup now looks like lay out your wires, hook up your acquisition unit. You had GPS, you could even have a satellite control, and it would record all the stuff on the digital, its own digital memory, and you just leave it there. And you put out 6 or 8 of them at the same time, record all day, all night long, and with no local noise source, the chances you're going to get great data are very high. So the wide induction coils were great. Static removal was just starting to come in then. Also EMAP, remember Carlos Torres? He had a way to basically smooth the surface with a spatial filter. So a lot of the stuff, the processing and coastal compensation and the train compensation stuff that they worked out was really quite powerful. This is an example of a lot of smart people working on the same problem for 20 years. And it worked. These days, this is not an unusual data set. The early days, we were basically 3 or 4 decades at the most. Now we're 6 decades, and sometimes more. I've seen it as high as 25K down to 1,000 seconds or 10,000 seconds, right? 36-bit. Now Zong claims a 36-bit data recorder, but actually it's 30, he says. That's 30 is fine. So it's a different world out there. MT is now pretty much the strongest and the dominant electrical methods for geothermal systems. It's got the penetration capability. You can collect it cheap. You can do 3D modeling and inversion with the stuff. You can with all the static correction, it dominates. It's the gold standard. The standard workflow these days, and then I'm going to get to the modern one. How am I doing with time? I'm seeing blowing through this. Yeah, I'm doing okay. The standard workflow these days, and this is some data I got permission to, so long as I don't show it with the geothermics, is collect your data, make the model of the technology separately, so long as it's geologically reasonable, and then start stacking them and making sure that the parts that you're putting in are consistent. And then so at least visually, you have to have a model where the dominant features agree with all your data. The gravity, the magnetics, the MT, SP if you have it. So at that point, you bring in the geology and the geochemistry, and your conceptual model fits all of it. So this is really a kind of a stack it on the table model that we're doing. A lot of it's more sophisticated now, and I've got an example of that coming up. But back then, now the standard workflow is a lot more effective. Project in Indonesia, which goes beyond standard workflow. This was data given to me by Randy Mackey in a paper. It's a large vapor dominated system in Western Java, presently about 300 megawatts, probably could go more than that. They did MT, micro earthquakes, gravity, et cetera, to map the porosity, the faults, and the resistivity. They want to find more resources here, but they want to manage and further develop the system. So gravity, micro earthquakes, the thing was popping like crazy. So a lot of times you get the micro earthquake data with geothermal fields for free. MT and surface resistivity and a lot of well data, advanced analysis, joint inversion, and a lot of borehole validation. The big deal with this, we can say all we want about our fancy models. They agree with the geology, et cetera. You start drilling holes into the geothermal system. If it still agrees, then you got something. So here is this well, this field full of wells here. You can see the resistivity from MT is actually a resistivity not super high, but pretty high, 50 to 100 ohm meters. So, whoa, what's that? So a lot of these vapor dominated systems, or at least the geothermal systems worldwide, the resistivity is high because the water is pretty fresh, it turns out. And a lot of it is steam, another high resistivity. So there's not a lot making to cause the resistivity to be low. So above the field, you see this low resistivity zone associated with highly evaporated hot springs deposits, where a lot over time you get high salinity brines because it's all evaporated, and a lot of thermal alteration. You see also this field, this particular area, the density is pretty high. Again, kind of a surprise, right? You know, you expect low density with some fractures, et cetera, but an intrusive body is high density typically. So it turns out that the high porosity within these bodies was the MEQ was the big deal to help find that, because the MEQ can help map density variations in addition to with the VPS ratio. And with that and the gravity, they were able to do a pretty nice model of the entire system with all the resistivity the density and the earthquake data, and they could get something that tied them all together, and they used it for joint inversion, and they actually got a reasonable fit to the data doing it that way. My experience with joint inversion has not been positive. Usually the data is something funny about one sets of the data, and you wind up fitting something and getting a lot of crazy models. So you really have to know what you're doing, and it's got to be good data in order to get something good. So with them knowing what they're doing, they get a much better model. So for example, the MT alone, you get this. And the joint inversion with the MT gravity and porosity from the seismics, you get that. So it's quite a bit different than it was before. So MT in the near, geothermal in the near future, and then what I'll do pretty much after this with one more little group, I'll turn it over to Bill. If you're willing to show your last 4 slides.
Sure.
All right, great.
Well,
So we're good.
Time done, okay.
We're good. Okay, so good and bad. First of all, a lot of the easy ones have been found already. We've been working on this for a while. We got all the big guys. And more remote spots, Indonesia and the Philippines, there's still stuff around. But in those cases, there's not a lot of people to build power plants, and there's not a lot of money to buy wells, right? So they're doing it some. Indonesia is starting to grow real quick right now, I understand, right? Management and monitoring is a big deal because there's a lot of heat still there. You know, if when you're doing a lot of the oil and gas for fracking, the big complaint is that, yeah, after you're done fracking and producing and the wells go dead, you've still got 90% of the oil there. All right, after the geothermal fields go dead, there's still like 98% of the heat there. So we're not doing a good job of mining the heat from the rock, because that's really our product here, is the heat. We're just using it to boil the water, either stuff that naturally comes or the stuff that we supply. So there's no law against supplying water. The geysers are still alive because we're getting water from Sonoma County and from Lake County, right? Without that, the geysers would be dry as a bone. So one thing now, Greg, you can say if I did some numbers here. A good geothermal well produces 20 million gallons of water a day. 20 million. Now you might lose 20% of that with evaporation to put in the other 3/4. But that means you're losing 5 million gallons of water a day per well, including Sundays, right? So this is all geothermal fields have the problem that they're pressure depleted, all of them. And their biggest problem is water. And you can't put in dirty old, crappy old salt water, because it would start precipitating stuff out so fast that you would kill all your flow. So water is the huge, so this year would be interesting up at the geysers. I don't know how much a change in pressure you're going to get with all this rainfall we've had, but I know that they've had changes in production over the years when they have heavy rainfall years. So now enhanced geothermal then becomes more interesting. What we used to call hot dry rock, just add water, right? It's an enormous resource. Developing could be expensive, but I look at analogously to fracking. You know, the wells, as Roland was saying, coming in cheaper than we thought because the rock is not crazy. But, you know, if you're drilling for geothermal in a normal geothermal field, every well is an adventure. Lost circulation drones, drilling into faults at too shallow a depth, having issues all over the place because every well is different than the previous well, and it makes the drilling really expensive. But hot dry rock, not so much. Same rock. You know, you figure out how to do it over time. You drill 8 or 10 rocks, wells into the same hard rock. You could probably figure it out. So example is this is the first one they tried was at Fenton Hill near the Valles Caldera. I did a year's worth of work there. What a gorgeous spot. What a beautiful spot. One of them. Collected a lot of pretty lousy data there, but it's a good spot, right? Did tellurics and MT. So Fenton Hill, which is adjacent to the caldera, was drilled into granite. They drilled 2 adjacent wells into the hot rock, and it costs a fortune. They didn't know how to do it. They didn't have a lot of fractures, but they ran out of drill bits. The drill bits just, it ate them up. The rock just killed them. The wells never connected very well. And I don't know how many millions of dollars are spent on this, but eventually they ran out of money and they never get anything successful out of it for power. Forge is looking a little better. It started by DOE couple of years ago, 3 years ago, something like that. They had one deep well, this 5832 well, and it was drilled into the bedrock. It's adjacent to Roosevelt Hot Springs right in here. Yeah, right in here. Which is a operating power plant, high temperature, 270 degrees centigrade. Again, pressure depleted, but in any case, it's an operating plant, I think 30 megawatts, 50 megawatts, something like that. So this one, they wanted to drill into the country rock adjacent to the Roosevelt, knowing it would be hot. And if it was competent rock, they were thinking, well, the drill, it's not a remote site, it's reasonable. Let's see how it works. They wanted the fracking technology is way better than it was in the 70s. You can orient your wells a whole lot better than it was we did in the 70s. The drilling technology is a lot better than it was in the 70s. So drilling into a high temperature hot rock is not such a horrible task anymore.
Or vertical wells?
They're horizontal wells. They're deviated wells that go about 1 kilometer. Yeah, highly deviated, like about 70 degrees, 75 degrees. They have a ton of vertical wells. Here's their site, a photograph of their site here. Their vertical well, horizontal wells go from here to here. One above, a producer above an injector, and they frack them 5 or 6 stages over how long? About 1,000 feet, Roland? Yeah, near the end. And so they're into this granitoid, hot rock, and you see the temperatures here. They're looking for temperatures 220, 230 degree range, right? And they're going to see if it works. A lot of the background data was under the control of Phil Wanamaker, who died last year. He was a good friend and a hell of a geophysicist. And not only that, a solid technical guy, was honest, and I'll miss him. He was a good friend. He was doing a great job on this as well. High precision gravity, high precision magnetics, high quality MT data, reflection data, micro earthquake arrays. Although they did a bunch downhole, and I guess they lost all their sensors. They could, every time they wanted to put a string of sensors down any of these holes, it would melt and they get nothing. That's correct, right?
Well, they collected quite a few data sets. But
They-
had problems with some of the geophones and problems with some of the gas rings.
So, but they do have a big arrays on the surface. However, you do need to get down to get
The surface to get about 10% of the seismicity.
Yeah. And so that seismicity is very, very important, as we found out with a lot of the other fields, right? Logging and coring, the data is modeled into a combined conceptual model. This was good stuff. And we're going to miss Phil, not only because I'm going to miss Phil personally, but he did a hell of a job on this. Everything had a clean technical window to go through. He was a guy you could bounce off technical ideas. If they made sense, they were done. Now it's not the case. The monitoring data, this is kind of the project I'm working on with Ed right now. This is this Japanese VEMP tool. Vertical electromagnetic profiling, what it stands for. It is a 3-component vertical and 2 horizontal sensors, magnetic sensors at the bottom. Good to, I think, low frequency to 1 hertz or less, I think, something about 1 hertz. They go up to like 150 hertz. Electronics, communication, orientation are right in this door flask sitting on top. So you amplify stuff. We got the tool from Japan, and of course, all of the electronics were from the 90s. And they ran on computers that no longer exist, with operating systems that no longer exist. So we actually converted it to analog. So right now the signals are coming up the wireline cable rather than being digitized and stacked down holes. So we stack them on the surface with a geode system. When you get down hole with the receiver, and this will work in a cased hole or an open hole, and especially if you use the casing electrodes as a source, the sensitivity goes way up. there's not much sensitivity to the fracts with MT on the surface or any other electrical method that you can imagine. But if you get this downhole, and we're literally within a few hundred meters of the frac right here, you can see stuff pretty well. So we're seeing things, changes in the fact of 15 and up to 50% on some of the models that we ran. And this is not a low resistivity body. This is rock that changes from 5,000 ohms to 250 ohms. So status right now, they're drilling the second well. And I'm not sure when they're going to frack. Ideas? We said fall.
End of the year.
Better get busy. So here is a simulation of their frac zone. As you can see, it's this not linear frac. It's not, you kind of make a jumble of the rock there. And because of that, hopefully holding together, we have enough volume to circulate some hot water and to get some heat out of it. I don't know what the production plans here, if they just plan to test it and turn it off, I don't know. But the concept is good. We'll be watching microseismics, they'll be doing well testing, we'll be doing the geophysical imaging, and we'll be watching the ground deformation. My last slide really is what is emerging. And then I'll turn this over to Bill. He's got 5 or 6 slides. Maybe I'll stop for a second for other questions before we do that. Okay. So what's changing now as we sit here is remote sensing and drone-based technologies are starting to emerge in geophysics worldwide. Our intermediate here, we have this airborne and ground ZTEM system, which is very strong. It's very good system, much better software and computers, a lot more emphasis on monitoring and management. And there will be more borehole technology coming to the fray. Now, this photograph is VEMP on its first deployment in Japan, and Ed was on this. He gave me this photograph, and this was in 90s, 95? Yeah, like that. All right. First, let me stop. Any questions on this tour from the audience? I'm not seeing anything.
Just a specific question about the geysers. You mentioned that grid tool that you lost when you put it in one of the wells of the geyser.
Yeah.
Which well was it? Do you remember? And how deep did you go?
It was a fell site tool. Well, it was I don't remember what particular area, but it was just, and we were starting to get some data. We could see some of the fractures fairly well. But I think the problem is that you couldn't turn off the flow. The thing was still, we choked it down and it was still steaming, venting at the surface. And I think all of the steam destroyed the tool as we were trying to log the well. It was just too hard to do that. So I think that was a problem there. And the tool had been used 3 or 4 times before that, but that was his last. I guess I didn't hear it. Bill, you want to lead the group, the last few?
Okay. A blockade over here. Okay, this slide actually, Gabe here is the person who was sort of helping lead this charge and actually at the technical end, actually leading the charge. And Paul Swearing at Sandia. A guy named Steve Sewell in New Zealand and I sort of cooked up the idea of using helitem, as a regional survey, then following that up with MT and gradient holes. So using the helitem, most gradient holes are wasted. So for example, if you look at this, this is a helitem survey covering the DOD lands, much of the DOD area in Nevada, where we could do a helitem survey, outlined in the sort of white dashed outlines, and then the helitem. How many kilometers did we end up doing on that survey? 1,800. About 1,800 kilometers of helitem. So it's an airborne time domain EM method, and we're getting typically something in the range of about where it was very conductive, about 20 meters, but in most of the area, we're getting 200 to 300 meters into the subsurface reliably. One of the key things here is that not the contractor, but the USGS has put together an inversion workflow that did a much better job on the depth of investigation assessment. So the inversions are very similar between the contractor and the USGS work. The depth of investigation assessments were much better and more realistic. And this is important to us if you're spending money, is where do you not know what's going on? And that's kind of a revolution for actually TEM in general. Is actually characterizing where you lose resolution is been what would you say optimistic, typically in the geothermal applications.
So, that model, what does it do about you have a lot of topography there. You have a lot, so I was wondering, is it all drape coverage or is it
It's drape coverage, but basically just one of the things also is choosing a place where this technique will work well. And as the survey progressed, they just stopped doing in basins in the middle. There's some gaps in this survey. In the midst of the basins where you have playas, you're only going to get down 20 to 50 meters. Stop surveying on playas, for example. This is an area down at a place called East Hawthorne with a weapons storage area. However, got very good data, tons of culture, both good MT and very good, and the helium was very good quality after a couple of tries to sort that out. Basically you can see the clay alteration. It's not alteration, it's mostly, these are mostly lake deposits. And then you have gravels on top of that. If you put a gradient hole and you have 150 meters of gravel, for example, all of these holes did not penetrate through the meteoric layer, so they're wasted at maximum temperatures like 15 Celsius. Whereas this hole here, which just gets into the clays underneath that, you get a conductive gradient that will tell you something about, when you extrapolate that, what's happening deeper. And demonstrated with a deeper hole over here that the Navy drilled. So this integrating that into a conceptual model when you get in the basin range. Out here, where you just see the middle of these clays, we did MT, the conductive zone goes a lot deeper. And the plan is where we can to drill gradient holes and eventually a slim hole to target geothermal system. So that is a then there's a bunch of tricks involved in that, but and then when we have a range like this, typically all the fracturing and so on in that is just carrying cold water to significant depth, and you're not going to get an attractive gradient hole or a reservoir. Then worldwide, MT has been commonly used to look for magma bodies. Most deep conductors that you get in volcanic areas turn out actually not to be, most of the time they turn out to be just noise and conversion problems. And so most of these have failed when people have drilled them. However, some of these, for example, this is an example in Tulamoy in Ethiopia. We've now had guys at ETH in Zurich, the Randy Mackey's group, CGG. Let's see, who else is that? Almost everybody, the folks in Brest, but everybody's had a SWAC at this particular data set and run an inversion. And this is a pretty much everybody agrees that this is a real conductor at almost drillable depths. The conceptual models for this, however, vary a lot. And that's actually putting together conceptual models when you have shallow magma. It's counterintuitive what happens. Shallow magma tends to counterintuitively suck a lot of cold water down to support that very hot water going up. And where it comes up and is going down is not obvious at all. It is a very counterintuitive thing, where the most recent volcano comes out, touches a hole in the clay cap. That's where the cold water comes down. Not what you would usually think, that your most recent volcanic feature would be the coldest spot. This is just an example, another example of, again, I think. I hope Matt Folsom is listening in here, but the general theme in sort of modern applications worldwide is that it is important to get the geophysics right and so on. But petrophysics is where the easy pickings tend to be right now anyway, worldwide. So, for example, in Turkey, there's a lot of geothermal wells that have been drilled on deep conductors. So just you see some big red blob there, and GGG's inverted a lot of these things, and then they tried to talk people out of drilling them, but you got to drill a deep red blob, and typically in Turkey, though, well, all of them in Turkey have turned out to be graphitic schist, and pretty cold graphitic schist as a rule. So there is on some of these geothermal. First they drill the graphitic schist, and then they drill the geothermal system. But some of these wells are 10 million. You can actually run out of money drilling the anomalies instead of drilling the models. This is an example where there is an elaborate petrophysical story about what this hole is. But I'm not going to, it's too elaborate. What I'm also going to point out is part of this thing is hydrology matters. And in this particular, this is the Rantau to that field in Indonesia. There's a water table sitting at that where the clay alteration that's sealing the reservoir is below the water table, where the reservoir is an outflow subboiling. Where the reservoir boils, and you get gas and steam into the above the water table, you get a flip in the clay cap where the base of the clay cap is above the water table or at the water table, and you can map that out and get the geometry of the hydrology of the field. And this is Gabe's. So I should give it, but this is to say, that's we've given a couple of examples. There are fields that have many working pieces with a petrophysical story for each of those. In this particular field, there was an argument that this was a vapor core, a magnetic core system, and that an outflow of that acid vapor core was what the origin of the field. The game here was to show that isn't true, because nobody wants to drill. There's been some very bad examples worldwide of people producing systems that are connected to an acid core that then turn acid. So banks have been burned. They don't want that. And in this particular case, you have the geochemistry said it's not the case, and the geophysics you can make support that case. And then there's, I guess, really, this is just the thing, is that you can get many moving pieces to these conceptual models. I recommend Gabe Matson's paper on the subject. Then microgravity monitoring. It's actually the key geophysical component here. The microgravity component really is Syntrex makes a CG6, go get one. And that's the story on the hardware end of things. The processing is really straightforward. The issue is, how do you use this data? And integrating the microgravity into the reservoir simulation has been the technology advance. And the simple intuitive application of it actually is often people don't quite get it. The assumption is that you're producing here and injecting here, the gravity will go up here and go down where you're producing, so you'll have a gravity low. And actually, the way these things work is that this reservoir is a permeable reservoir. When you're producing and injecting, the pressure equilibrates reasonably quickly. There will be a gradient, but generally speaking, if on a typical reservoir, you're gradually reducing the mass in the reservoir because stuff is being evaporated out of the cooling towers, and that mass loss creates your gravity change. That gravity change creates that mass loss also creates a pressure change in the entire reservoir, and where the reservoir is close to the boiling point, it makes a steam cap, and that steam displacing water is the gravity signal. it happens, this reservoir will be close to the boiling point right at the apex of the system. So you get the gravity decline, not when you're producing and injecting, but where you're close to boiling in the reservoir.
Are there geochem markers that go along that they are helpful in?
Actually, the interpretations of the gravity that you might call naive for many geothermal groups, they ignore the gravity because they're sort of saying, well, the gravity is declining, something's wrong. Many companies think there's something wrong with the gravity because it's not matching kind of their expectations. Often the geochemistry and simply the production, the enthalpy of the wells, there's all kinds of information telling them what's going on in fields. And this kind of field, this is after a real field. Only these wells were producing relatively deep entries. They didn't see the steam cap. And so they didn't know what was being created until they eventually popped a well over here. And this is where they want it, because then you don't need any injection. You just produce that steam cap. Half your cost goes away. So if you know you have a steam cap, it's a good thing to know about and know the geometry of. If you don't happen to have wells in your steam cap, microgravity is the only way at probably many times greater cost. You could get the similar information from inverting earthquake, VSP analysis and things like that. But collecting the data set and analyzing it's going to cost, I don't know, 10, maybe 100 times what the gravity is going to cost you. So this is the TV geothermal field, and then just the red is the outline of the field. They start production, you start seeing the gravity decline where the initial production is. They keep on producing, you see the gravity decline here. There's an east and a west part of the zone is in these two fields. They start producing, you start more boiling in the east and west part of the field. At this time, the cold water started, it's connected to a meteoric water source, just a very large aquifer, a regional aquifer, where it starts dumping into the eastern reservoir. So the gravity stops changing. The gravity in the west continues to change. Bring it up into roughly 2000, this area is completely resaturated. And this area has now been the focus of all of the production. Whoops.
Yeah, one more.
Oh. Okay, I'm just going to show that there. So from that, what used to be done is people would do Gaussian integration to do mass balances and stuff like that. The errors in those integrals were essentially bigger than the signal almost all the time. What you can do instead is simply the simulation that you're doing, the reservoir simulator computes the steam saturation and the water saturation and so on. So what the current standard, or I would recommend the standard to be, is to constrain the saturation modeling in the reservoir with the gravity. And when you match that, you end up being able to match many components of this. And for some reason, this has turned out to be micro text here. But basically, the boundaries of the system can be constrained, the fracture spacing and things, the parameterization of how water is boiled out of the pore space. These are called the Mink parameters. These things are basically almost unconstrained. People would just take guesses, and if it fit, they say good. But they can get reasonable constraints on these parameters in fields that are boiled.
Yeah, and remember the recharge.
And I said, yeah, and
completely-
boundaries.
Yeah, well, what I mean is your mass balance is completely unconstrained.
Yes.
You have to guess how much is being recharged. The microgravity gives you a complete or a very good stream.
And then the final, this will have to be the final slide because we're running. This is Steve Sewell's micro earthquake study of the Darajat, the Rotokawa field in New Zealand. The I could have showed one, I should have thought of that. Greg has an equally interesting example from Salak in Indonesia, where in this case, they're injecting here, producing here, and the concern was that they'd have to move this injection to way up here, crossing the Waikato River, and the cost of this was going to be about $80 million. So the concern about how fast the injection moved was a high value decision point. When they started injecting, the seismicity started up and stopped. And the immediate question is why? Then they did a bunch of geology, geochemistry, all kinds of things were done to sort this out, not just seismicity, but the seismicity stopping at a line caught their attention. And it turns out there's a central field fault that was missed. It's one of those things that everybody sees it now, even at the surface, but it didn't appear until the seismicity stopped at that line. And so the seismicity is hitting the central field fault, is permeable along strike and impermeable across strike. And so it's basically distributing the injection along this, basically along those axes. And it's not getting to the production, which means there's actually it is now the model is that they hit a still point with the injection, and they are seeing some injection come back, but this is from 2004 to they got 20 years where they got free injection. Maybe they'll have to move it now, but 20 years in terms of present value is huge. So I think that's great over time.
Well, I think that's great. These are cool. So now I would like to invite, I have one more slide. Let me go to slideshow. Two people chatting here. Right. That's it. That's fine.
That's it. There you go.
That's it. Last slide.
There we go.
Present production in the world is around 8 gigawatts, right, for geothermal power. That's 8 nukes or 15 gas plants, but almost half of this is in the US. Although Indonesia, as you've been hearing, Indonesia, they're growing quite a lot. Local power generation is emerging, so I look forward to the day where you can have the small town in Nevada have their own little geothermal power station, and the 10 megawatts will give them everything they want, right? That would be nice. They don't have gigantic national power lines going everywhere. But of course, a few solar panels could do the same thing. Geothermal heat pumps are interesting. This is Ed's soapbox. He says, well, there's plenty of heat in the ground. You know, we don't have to get real fancy. We can just take care of a lot of our heat and electricity needs just by being clever with the local ground that we have outside the door. One of the issues is natural resources are not always located where the power and the money is needed most. So they can have a lot of power generation in Indonesia, but they don't have any money. Is geophysics important? Has it proved important? Yes. And I think even more so. So I invite anyone, we have a couple chats here. We have 14 people remaining. Any comments from the peanut gallery out there? I mean, or in here. Okay, not technical. All right.
All right, well, there's nothing formal.
All right, just any,
I'll say, let's go ahead and thank Mike for giving this talk. We really appreciate it.
and Bill,
We will be, for those of you online, thank you for sticking around. For those of you in person, we will be adjourning to Laval's afterward for pizza and beer if people would like to come. So feel free to ask Mike more questions then.
Okay, all right,
All right, thank you.
all right.
Familiar with Furbo's wells?
Excuse me?
Familiar with Furbo's wells?
Yeah.